Okay, welcome back. It's time to get going again. If you've totally forgotten about what's happening in this course, be reminded that the next exam starts a week from today. With that in mind, we're going to have an exam review this week, Friday. So if you elect to come to this, you'll get to see me 3 times this week instead of 2. And it'll be 1 p.m. in this room. Alright, so again, it's optional if you want to come. It will be recorded and put on YouTube. And the file that we'll be going over that has all is a mock exam with 20 questions like the real exam is, that's already posted in Blackboard. You can find it there, and then after the review I'll post the solutions and everything. Alright, so we'll have one of those this time. I will be around. And if you kind of took a break from chemistry over spring break, it's time to get back into it. It's almost showtime. So we're going to finish most of chapter 6 today. We have a couple things we'll have to clean up on Wednesday, but that will be the end of the exam material. Alright, so what we ended with last time was a discussion of 2 types of aqueous reactions. We did precipitation reactions and acid-base reactions, and we kind of separated them into 2 categories. We should recognize that there are a lot of similarities between the 2 because they involve exchanging ions in aqueous solution. And what we're going to show in this example that I'm going to start with is the possibility that acid-base reactions can also involve precipitations. They're not necessarily 2 separate processes. In most acid-base reactions, precipitation does not occur as well, but there are cases where that happens because if we recall, one of the products of an acid-base reaction is an ionic compound, and if that ionic compound is insoluble, it will precipitate from solution, even if the initial acids and bases that you started with were soluble species. So let's look at one here where we want to write the Ionic equation when phosphoric acid and calcium hydroxide react with each other and identify the spectator ions. Alright, so what we're going to do is take the 2 reactants, H3PO4, so we need to be able to translate names into formulas. So phosphoric acid is H3PO4, it's PO4 3-, so it needs 3 hydrogens to balance the charge, and then calcium hydroxide is going to be CaOH2. On the periodic table you would see that calcium forms 2+ cations. Alright, and then just like any acid-base reaction, the 2 products of this, acid plus base, gives us water and an ionic compound. So the OH- from the base and the H+ from the acid combine to make water. And then the ionic compound that forms is going to be calcium with phosphate. And so the correct formula for that would be Ca3PO4 taken twice, because it's 3 2+ cations, 2 3- anions. So these are reactants and products, and we need to balance things. So one easy way to balance, as I said, for acid-base reactions is look at the number of protons that are involved and look at the number of OH- that are involved. Our acid here, H3PO4, has 3 acidic protons. Our base has 2 hydroxides, OH2, and those have to react in a 1-to-1 ratio. So you have 3 protons, 2 hydroxides. The only way to deal with that is to put a 2 there and a 3 there, so that we now have 6 of each, 6 H+ and 6 OH-. That will then form 6 waters. And then making sure we have the correct balancing here, we have 3 calciums, so that's already balanced, 2 phosphates, so we don't have to add any coefficient to this compound here. Now we sort of neglected putting some of the symbols on here, so the 2 reactants in aqueous reactions are always dissolved ionic compounds, water is a liquid. But then thinking about this other product here, calcium phosphate, remember that pretty much all phosphates are insoluble unless they're paired with a group 1 cation. We need to think back to our solubility rules that we covered last time. But phosphate salts are typically insoluble, and calcium phosphate being a classic example, so that's going to form as a solid. So this is an acid-base reaction that also involves forming a precipitate because the ionic compound we form is not soluble in water. Okay? So that's the full equation, but what we want here is the net ionic equation. So when we want to write net ionic equations, we split up all of the species into ions that are appropriate to do so. So if we think about H3PO4, is this a strong acid or a weak acid? Alright, it was a decidedly numb response to that, but it's a weak acid. Okay, so we have to learn there's 6 strong acids. It's HCl, HBr, HI, and then nitrate, perchlorate, and sulfate are all strong acids. So learn the strong acids. Everything else we would assume is weak, and phosphoric acid is one of the common examples of a weak acid we'll see. Our base, calcium hydroxide, is a soluble ionic compound, so we're going to split that up into ions when we write the ionic equation. This is a liquid, so it's not going to be split up. It's a covalent compound. It doesn't ionize at all. And then this is going to be, as we said, insoluble because it doesn't follow because of solubility rules, and we put a little S next to it. So when we want to write the ionic equation, the only thing that's going to actually get split up into ions is calcium hydroxide, because that's the only soluble ionic compound. Remember, weak acids, we don't split them up into ions because only a very small portion of those actually dissociates. So we're going to write H3PO4 just like we had it. We'll split up the calcium hydroxide into 3 calcium, 2 plus. And then we have 6 OH minuses, because we have a coefficient of 3, and then there's 2 hydroxides per calcium hydroxide, so we get 6 OH minuses. So that one gets separated, but then on the product side, we're not going to separate anything because, as we said, water is a covalent compound, a liquid. And then anything that's insoluble, we also don't want to split up into ions, so we just write it like this. So the only thing that gets separated into ions is calcium hydroxide, which is a soluble ionic compound. And we notice here that there are no spectator ions, because there are no ions that appear on both the left and the right side. We have calcium 2 plus as an ion on the reactant side, but that doesn't appear on the product side. OH minus is on the reactant side, but there's no OH minus on the product side. So this is a rare example of an ionic equation that has no spectator ions. Everything is involved. Every ion is involved in the net reaction. And so what that means then is that that equation we just wrote, which is the total ionic equation, is identical to the net ionic equation. If we wanted to get to the net ionic equation, we would have to cancel out the spectator ions, but there are none in this case. Alright, so this is the net ionic equation, the one we wrote. There are no spectator ions, and that's as simple as we can write it. So this was an example of an acid-base reaction accompanied by precipitation, and then we also had, because of that, very few, or actually no spectator ions and only a couple of ions that actually participated. Okay, any questions on that? Alright, so I don't want to treat this like it's some brand new topic. Just whenever you're writing an acid-base reaction, you have to think about whether the ionic compound that forms is soluble or not. That's another sort of thing that goes into it sometimes, although in most cases it's not an issue. Alright, then the next one I want to go over is just one last example of balancing an acid-base chemical equation. So we have sulfuric acid and lithium hydroxide. We want to know how many moles of water are formed when the reaction is balanced with the smallest possible whole number coefficients. So just like before, we have to write out the reactants and determine what the products are. H2SO4 is sulfuric acid, and then lithium hydroxide is going to be LiOH, and we form water and an ionic compound. So the ionic compound is going to include lithium from the lithium hydroxide, sulfate from the sulfuric acid, so the correct formula for that would be Li2SO4. And this one is a soluble compound. All lithium salts would be soluble, so it's not going to be one that forms a precipitate in this case. But really what the question is simply asking is how many moles of water are formed. So we don't even really have to write out the full balanced equation for this question here, although it's good practice to do that. And so again, the shortcut that I like to use in finding the number of moles of water is to keep in mind that each OH minus that we have has to react with one H plus. And so if we look at our acid here, it has 2 H pluses. It's H2SO4, so 2 acidic hydrogens. Our base has only 1 OH minus. It's just lithium hydroxide, 1-to-1 salt. And so if we want to balance these out, we have 2 H pluses reacting with 2 OH minuses. We need to put a coefficient of 2 there. And then if there's 2 each of H plus and OH minus, we form 2 moles of water. Okay? And this, again, would not have a coefficient, but we don't really care about that. What we care about here is this coefficient of 2. So we would form 2 moles of water in this reaction. because our acid has 2 acidic hydrogens, so we need to react that with 2 OH minuses. And every time 1 H plus and 1 OH minus combine, we get 1 water. If we're combining 2 of them, we get 2 waters. So that's how we would approach that one. All right, any last questions on acid, base, or precipitation reactions before we move on to the third and final category of aqueous reactions we're going to discuss? All right, so the last thing we're going to talk about are called redox reactions, which is shorthand for reduction oxidation. And so let's look at what's going on here. So whenever we have a redox reaction, we're going to have some species, one of our reactants is going to get oxidized or is going to be involved in oxidation, and another one of our reactants is going to get reduced or involved in a reduction reaction. And so what we have here are in a redox reaction is transfer of electrons. So basically one species loses electrons and it transfers its electrons or some of its electrons to another reactant in the chemical reaction. So the oxidation refers to loss of electrons. So whenever something gets oxidized, it means it's losing electrons. Reduction is gaining electrons. All right, electrons cannot be created or destroyed in a chemical reaction, so whenever you have one of these, you have to have the other. You can't have oxidation without reduction or reduction without oxidation. And when the two happen together, we call that a redox reaction. Reduction, oxidation. So a redox reaction is a reaction that involves transfer of electrons. So we should keep in mind that Chapter 6 is all about aqueous chemical reactions. Redox reactions do not have to occur in water, but very often they do, so that's why it's grouped into this chapter, as we'll see. But it's any time you have electrons transferred between reactants in a chemical reaction. And really, precipitation reactions, acid-base reactions, redox reactions, those three categories make up every chemical reaction known. So you can classify any reaction as one of those three. And so any reaction that's not precipitation or acid-based would fall in the redox category, even if it's not obvious that that's the case. We're going to learn some more systematic things about how we classify redox reactions and especially how we balance them, which is going to be the big thing that you'll have to do on the exam. Okay, so you have loss and gain of electrons. If you want to remember which one is which, is oxidation losing electrons or reduction gaining electrons, think of a lion, which I think the Latin root for that is Leo. And what does a lion say? It says gur. And so if you lose electrons, that's an oxidation. So that's Leo. And what does Leo say? He says gur. And so if you gain electrons, that's a reduction. All right, so hopefully you'll never forget that, but that's the difference between oxidation and reduction. But like I said, in a redox reaction, they will occur together. They will always occur at the same time. You can't have one without the other. All right, so that's kind of some key terminology. Let's look a little bit then at how do we decide in a chemical reaction, first of all, is anything getting oxidized or reduced? And then if we determine that, which reactant is getting oxidized, which reactant is getting reduced. In other words, how do we keep track of electrons in a chemical reaction? Because in the chemical reactions that we write, you never see electrons written as a reactant or a product. So how do we know if electrons are being transferred between reactants and products? The way we do that is with what's called oxidation numbers. All right, so what we first have to learn in this is how to assign oxidation numbers, and that's going to then allow us to determine if something is getting oxidized or reduced in a chemical reaction, because whenever something gets oxidized or reduced, its oxidation number changes. So we have to learn how to assign what that is. Oxidation number is kind of like formal charge. We learned about formal charge a while ago, but it is a bit different. So if you recall from what we did with formal charge, what we were doing was we were taking two atoms that were bonded to each other, and we were taking all of the shared electron pairs, all of the electrons that are involved in the bond, and we were dividing them up equally between the two atoms. And then we were calculating a charge based on that. And then any lone pair electrons would belong to that atom itself. That's what we did for formal charge. Oxidation number is a little bit different. What we do for oxidation numbers is when you have a bond between two atoms, all of the electrons go to the more electronegative element. And then we divide electrons up that way and determine the charge that way. But in reality, instead of thinking about it that way, there's just going to be a set of rules that we want to learn that allows us to quickly identify oxidation numbers without having to remember electronegativities all the time, without having to split up the electrons and all that stuff. So here's a set of, I have it listed as 8 rules that we can follow for determining oxidation numbers. Many of these are very common, some of these you'll almost never use, but if we learn these 8 rules and kind of get a lot of practice with them, we should be able to quickly assign oxidation numbers for any element. So basically each element in the chemical reaction is going to have an oxidation number assigned to it, and that's what we're going to first learn how to do. Alright, so the first one that we should keep in mind is that if you have an atom that's part of a neutral element, just a simple pure element without any sort of chemical bonds to other elements, or no charge associated with it, if you just have an element, the oxidation number is going to be 0. Okay, so if you have, for example, metallic sodium, just Na by itself, oxidation number is 0. If you have O2, which is a diatomic element, 2 oxygen atoms, both of them will have oxidation numbers of 0. So as long as it's just a pure element with no charge, the oxidation number is 0. And the other nice thing too is if you're asked to identify a redox reaction, is this or is this not a redox reaction, any reaction that involves an element is going to be a redox reaction, because the only time the oxidation number is 0 is when it's a pure element. So if it's changing into something else as part of that reaction, its oxidation number will change, and that means it has to be a redox reaction. So look for pure elements first of all when you're doing this, because those will have oxidation numbers of 0, and those will allow you to quickly identify the reaction as being a redox reaction. Alright, other species that are pretty easy to assign. If you have a monoatomic ion as part of the reaction, so if we have Na plus, if we're doing an aqueous reaction, or Cl minus, or any ion, the oxidation number is just equal to the charge. Okay, so oxidation numbers can be positive or negative. So for Na plus, the oxidation number would be +1. For Cl minus, it would be -1. And so if you know the charge, if it's just a simple ion in solution, then the oxidation number is equal to the charge. Another important rule that a lot of these then follow through is that the sum of the oxidation numbers in a compound or in a polyatomic ion equals the total charge. So if you have a binary ionic compound that has positive and negative ions in it, the positive ions will have an oxidation number that's positive, the negative ions will have oxidation numbers that are negative, and then those two would have to add up to be 0, just like they would for any ionic compound. So whenever you have a compound that has more than one element in it, the sum of the oxidation numbers has to equal the total charge. Whether if that's a neutral compound, it would be 0, or if it's a polyatomic ion, it would be whatever the charge of that ion is. Alright, and then extending from that, if we have an ionic compound, the metal in the ionic compound will always have a positive oxidation number. So On is the abbreviation for oxidation number, and that's going to be equal to whatever its charge is in that compound. So if you have an ionic compound with any group 1 element, it would have a +1 oxidation number. An ionic compound with any group 2 element, that element would have a +2 oxidation number, or if it's a transition metal, it's going to vary depending on what the charge is in that compound. But whatever the charge of the metal is, that's the oxidation number. Rule 5 deals with hydrogen. So hydrogen has 3 possibilities. If it's just elemental hydrogen, H2, it would be 0, just like any other element. But then hydrogen only has 2 other possible oxidation numbers. It's +1 when it's bonded to a nonmetal. So basically any covalent compound with hydrogen, the oxidation number for hydrogen will be +1. So that's another one that you want to assign right at the beginning, because that's pretty much invariant. The only exception to this, which we haven't seen many examples of, is that it's -1 when it's bonded to metals or metalloids. When hydrogen is bonded to a metal, we call it hydride. where it behaves like an anion. And so there are a few compounds we'll see like this. The metalloids primarily being boron and silicon that hydrogen would bond to. So if you have BH3, boron trihydride would be one way to name that, or borane is the common name. In that compound, because the central atom is a metalloid, hydrogen would be -1 oxidation number. So hydrogen is almost always +1, but there are rare examples with metals and metalloids where hydrogen is -1. All right, another element that has pretty much an invariant oxidation number is fluorine. So we said that oxidation numbers are assigned by giving all of the electrons to the most electronegative element in the compound or in the bond. Well, fluorine is the most electronegative atom on the periodic table. So whenever we have a bond with fluorine, it's going to get all the electrons and it's going to have then a -1 oxidation number. So whenever fluorine is in a compound, so really the only exception to this would be F2, elemental fluorine, where it's still 0. But if you have any compound that contains fluorine, whether it's an ionic compound or a covalent compound, fluorine will have a -1 oxidation number. Oxygen is another one that's almost always the same. So oxygen is also very electronegative, so it tends to hog electrons as well. And so most compounds with oxygen have -2 oxidation numbers, unless the oxygen is bonded to another oxygen or fluorine. All right. So if you have, well, O2, of course, is elemental oxygen. That would be a 0 oxidation number, like any element. But if you have a compound with an OO bond, like hydrogen peroxide, for example, the oxidation number will be, in that case, -1, not -2. And if you have oxygen bonded to fluorine, fluorine would be -1, and then oxygen would be something other than that to balance out the oxidation numbers. So there's few exceptions with oxygen, but it's usually -2. And then finally, if you have the halides, chlorine, bromine, iodine, the other halides besides fluorine, other halogens, these are almost always -1, except when they're the central atom. So there are compounds and ions that have one of these as the central atom, in which case the oxidation number will be something other than -1. Or if these are bonded to oxygen or fluorine. So the way we typically look at assigning oxidation numbers is we find one of the elements in there that has an invariant or very obvious oxidation number, and then we use rule number 3, the sum of the oxidation numbers equaling the total charge, to find the rest of the ones that could be variable. So especially the central atom, when you have these sort of AXM type structures that we've been dealing with a lot, the central atom can have a lot of different possible oxidation numbers. And typically the way you do it is you assign the oxidation numbers of the outer atoms first, which usually fall into one of these obvious categories, if it's hydrogen, oxygen, or a halogen, and then from there you go and do the central atom as the last one to balance out the charges. All right, so this is the set of rules. I don't want you to memorize these word for word, but we just want to get used to how we use them. So let's just do several examples of determining oxidation numbers. So let's say we have sodium sulfide. So we have to find the formula for this compound. So sodium is in the first column of the periodic table. All right, so sodium is in the first column, so it tends to form +1 cations. That should be very familiar by now. Sulfur is group 6A, so it's going to form an anion with a -2 charge. All right, so those are the charges, Na+, S2-. And then if we want to make a neutral ionic compound with those ions involved, it would have to be Na2S. 2 + 1 cations, 1 - 2 anion. But what we really were interested in here were the oxidation numbers. So the oxidation numbers for ionic compound are just the charges of the ions. So sodium in any ionic compound has a +1 charge. If it's just a sulfide compound, sulfur is a monoatomic anion, that always has a -2 charge. So those are the oxidation numbers for sodium and sulfur in sodium sulfide. So for ionic compounds, especially binary ionic compounds, it's relatively simple to get oxidation numbers. It's just the same as getting the charge, which we've known how to do since chapter 3. If we want to verify, as we said, that the sum of the oxidation numbers equals the total charge. Sodium sulfide is a neutral ionic compound, and so we have two sodiums, each with a +1 charge, with one sulfur with a -2 charge, and that sum, as we already verified, equals 0. So in any ionic compound, if it's a neutral ionic compound, the sum of the oxidation numbers has to be equal, and they're just equal to whatever the charges is of those ions. So in this case, oxidation number is nothing different than just the charge. But for other ones, it's a little bit more complicated. So let's do this one, phosphoric acid. We saw a reaction with phosphoric acid earlier. So we need to be able to turn, again, the name into the formula. Phosphoric acid comes from the polyatomic ion phosphate, which is PO4 3-. And so the acid with phosphate, as we saw earlier, is going to have 3 acidic hydrogens. So it's going to be H3PO4. Okay? So what we have here is this formula. We want to find the oxidation numbers. So we have hydrogen, we have oxygen, and we have phosphorus. All right, hydrogen is the obvious one that we start with, because anytime hydrogen is in a compound with other nonmetals, it's always +1. So this is a covalent compound with all nonmetals, so hydrogen will have a +1 oxidation number. So we can put that down already. Oxygen, unless it's bonded to oxygen, is going to have a -2. Maybe that's not so obvious, but if we draw the Lewis structure of phosphate, we should recognize that there are no OO bonds. So phosphate has that structure, and then if we put the hydrogens on, this is the structure of phosphoric acid. So there are no oxygen-oxygen bonds in this compound. Really, the only compound we want you to be familiar with that has oxygen-oxygen bonds would be either O2 or H2O2. Both of these have OO bonds. Any other compound that has multiple oxygens, you wouldn't really want to assume that there's an oxygen-oxygen bond unless we told you or showed you that. So there's no OO bonds, and what that means is anytime oxygen is bonded to a nonmetal besides itself or besides fluorine, its oxidation number is -2. So we can assign that one. But then phosphorus, which is our central atom, is going to have a variable oxidation number. We don't know what it is off the bat. Phosphorus can be a lot of different things, as it turns out. So to find that, what we want to realize is that the sum of the oxidation numbers equals the charge. So the sum of the oxidation numbers has to equal 0 because it's a neutral compound, phosphoric acid. And we want to find what the oxidation number of phosphorus is. All right, so we have 3 hydrogens. Each one is +1. We have 4 oxygens. Each one is -2. And then we have 1 phosphorus, which has whatever oxidation number it has. And so a little bit of algebra here. We solve for the oxidation number of phosphorus. We have +3 -8 is -5, so we need phosphorus to be +5 so that the sum of all the oxidation numbers equals 0. Okay? So phosphorus in this compound is +5. Another helpful thing to keep in mind with oxidation numbers is that the highest oxidation number that a main group element can have is its group number. Phosphorus is in group 5, it will never have an oxidation number above +5. Okay, so if you go above, if you ever get a phosphorus compound that you calculated to be +6, well, you messed up somewhere. It can't happen. But in this case, the way we find it is because it's the central atom, because phosphorus is one of those elements that's highly variable in terms of its oxidation number, we do the other ones first, the obvious ones, and then we use a little bit of algebra to find out what that oxidation number has to be. Okay, questions on that one? All right, the last one of these is very similar. We have the sulfate anion, which is SO4 2-. And we want to find the oxidation number for each element in this ion now. So 2 elements, oxygen, sulfur, and that's going to be what we're finding the oxidation numbers of. So just like before, there are no oxygen-oxygen bonds. Oxygen is bonded to sulfur in this case, so we know right away that it has a -2 oxidation number. Oxygen will almost always be -2. There's just a few exceptions to that. And then in this case, we just need to find the oxidation number of sulfur using the same approach. We don't know what it is off the bat. It's variable in sulfur-containing compounds. It can be a number of different things, but the total charge has to equal the sum of all the oxidation numbers. So the only difference here is that this is an anion, so it has a non-zero total charge, -2, as we know for sulfate. And that has to equal the sum of the oxidation numbers for oxygen and sulfur. So we have 4 oxygens, each with a -2 oxidation number. We have 1 sulfur in the center. And so what does that have to be for the sum to equal -2? So -8 plus what equals -2? That would be +6. Alright, so sulfur, again, it's a group 6 element, so it can't be higher than +6, and in this case it also has its maximum oxidation number of +6. So just remember, if we're dealing with charged species, the sum of the oxidation numbers won't equal 0, it'll equal whatever the charge is, in this case -2. Alright, questions on how we assign oxidation numbers. Alright, the next thing to talk about, I believe, is how to identify redox reactions and some other features about them. So these oxidation numbers that we've now learned how to assign play a key role in oxidation reduction reactions. Because in order for a reaction to be a redox reaction, oxidation numbers have to be changing. If the oxidation numbers of the reactants and the products are identical, it's not a redox reaction. And within that, we also have to define what are called oxidizing and reducing agents. Now, this is always a little bit confusing at first, but the oxidizing agent these are always reactants that we're talking about. We never define products as being oxidizing or reducing agents, but oxidizing agent is the reactant that gets reduced. Which always sounds confusing when you first say it or write it. You know, the reaction that gets reduced is the oxidizing agent. The reason for that is think about what the word, it's in a redox reaction, I should say, to complete the thought. But think about what an agent is. An agent is someone or something that does something. You know, if you're an agent of change, you're bringing change to the world in some way. So the oxidizing agent is the one that does the oxidizing. So that's why it's getting reduced. Because in most redox reactions, you're going to have 2 reactants that are involved in the redox transformation. One of them gets oxidized, one of them gets reduced. There are some other categories that are a little bit different than that, but in general, you're going to have one reactant that gets oxidized and one reactant that gets reduced. The reactant that gets reduced is the oxidizing agent because it's causing the other reactant to get oxidized. And the way we identify this is that the oxidizing agent, which gets reduced during the reaction, is the one that has its oxidation number decreasing during the reaction. Alright, so if we find that on the reactant side, the oxidation number is higher than it is on the product side for a certain element, that element is then part of the oxidizing agent. Now keep in mind, another little slight source of confusion, but we don't want to dwell on it too much, is that the words oxidizing agent, reducing agent, they apply to the entire ion or compound that that element is part of. So even though usually only one element gets oxidized or reduced, the entire species that that element is part of is classified as the oxidizing agent. So for example, if we had sulfur and sulfate, which is +6, as we just saw, if that gets converted to sulfite, the oxidation number changes to +4. So sulfur is getting reduced from +6 to +4, but we would say that sulfate, the entire species that sulfur is part of, is classified as the oxidizing agent. So these words refer to whole intact reactants, not to just individual elements. Alright, we'll see that in a second when we do some examples. And then finally, the reducing agent is the opposite. It's the reactant that gets oxidized or does the reducing. And just like you can't have oxidation without reduction, you can't have an oxidizing agent without a reducing agent. There will always be one of each. In rare cases, the same species serves as the oxidizing and reducing agent. We call that a disproportionation reaction. But in most cases, you'll have 2 separate things. One's the oxidizing agent, one's the reducing agent. You'll have one of each. Alright, so the reducing agent is the species that does the reducing, which is why it's getting oxidized. Or in other words, it's transferring electrons, it's losing its electrons and giving them to something else. And because of that, its oxidation number increases during the reaction. So whatever species has its oxidizing number increase, is going to be the one that is the reducing agent. Okay, so that's kind of some other terminology. So some types of questions we would ask you would be, let's look at a chemical reaction here. We're going to take phosphorus trichloride, react it with oxygen to make POCl3. And the first question is this a redox reaction? And the second question is, if so, what is the oxidizing agent? Okay, so these are typical types of questions we could ask you, identifying redox reactions, and then once you know it's a redox reaction, identifying the oxidizing or reducing agent, or in some cases both. Okay, so we have this reaction here. So the first thing we have to do to determine if it's a redox reaction is identify or assign all of the oxidation numbers. Okay, so for PCl3 we have phosphorus is our central atom. So whenever chlorine is not the central atom, it's going to be -1 when it's in a covalent or ionic compound. So if we have 3 -1s from chlorine, phosphorus has to be +3 to balance that. Remember, we ignore the coefficients when we're assigning oxidation numbers. Coefficients tell us we have 2 moles or 2 identical copies of PCl3, but the oxidation number just applies to PCl3 itself. It's not affected by the coefficients. O2 is a neutral element, so we can quickly identify its oxidation number as 0. Anytime it's just a pure element, it's 0, no charge. And then finally in the product we have POCl3. Chlorine is still one of our outer atoms, so it's going to be -1. Oxygen is bonded to phosphorus, so it's going to be -2. And then finally, if we have 3 -1s and 1 -2, this has to be +5 to balance those out and have them equal 0. So I did that kind of quickly because I don't want to spend too much more time on this. But again, the sum of the oxidation numbers has to equal the charge, which is 0 for this compound. 3 -1s, 1 -2, those ones we assign very quickly, and then the +5 comes to balance those out and give a sum of 0. So what we notice, if we're asking about choice A here, is this a redox reaction? We see that phosphorus in this reaction goes from +3 to +5. Phosphorus is +3 on the reactant side and +5 on the product side. Oxygen starts out at 0. And I think this reaction, it is balanced already, but anyway, oxygen starts at 0 and goes to -2. So because we have oxidation numbers changing, this has to be a redox reaction. I already introduced earlier a little bit of a shortcut. Any reaction that involves an element will be a redox reaction. Because O2, the only time it has an oxidation number of 0 is when it's O2. And so if it's changing to anything else, it's going to have to change its oxidation number, so it must be a redox reaction if you have a pure element involved. But we can assign oxidation numbers to allow us to determine that clearly. And then finally, what the choice B, part B is, what is the oxidizing agent? So we have to remember that the terminology is a little bit weird. The oxidizing agent gets reduced, which means its oxidation number decreases. So if we look at oxygen, as we said, oxygen goes from 0 to -2. Its oxidation number is decreasing, getting smaller or more negative. And so that means the reactant that oxygen is part of, O2, is the oxidizing agent. So we said that oxidizing agent refers to the entire compound that it's part of. So that means it's O2. Okay, remember, products can never be oxidizing or reducing agents. So if you're asked to identify an oxidizing or reducing agent, it's going to be one of the reactants. In this case, the reactant whose oxidation number decreases will be the one we identify as oxidizing agent. Okay, questions on that? All right, let's do one more like this. We have, in this case, the product of that reaction, POCl3, reacting with water to make phosphoric acid and hydrochloric acid. And we want to know if this is a redox reaction. So again, we have to identify oxidation numbers to see if any of them are changing. Now, we could also look at this first and see, does this look like the typical type of acid-base or precipitation reaction that we talked about last week before spring break? Does this look like an acid-base reaction to any of you guys? Someone said yes, so they're smarter than I am. It doesn't look like a typical acid-base reaction. It's not obvious that that's the case. We don't have an acid and a base reacting with each other to make water and ionic compound. So it's not obviously an acid-base reaction. So let's assign oxidation numbers and see if in fact an oxidation reduction reaction. So we saw last time in the last problem that in this compound is +5, -2, and -1. Those are the oxidation numbers for phosphorus, oxygen, and chlorine. Water, which is going to participate a lot in redox reactions. If we have any covalent compound with hydrogen, hydrogen has to be +1. Pretty much every covalent compound with oxygen is -2. So if you see water, assign the oxidation numbers as +1 and -2 as quick as you can and be done with it, because you'll see that a lot, and that's one that's very obvious. And then if we go to H3PO4, I think we did this one earlier also, and we saw that the oxidation number for hydrogen was +1. It's a covalent compound with hydrogen. A covalent compound with oxygen is going to be -2, and that left us at +5 for phosphorus. So that was another one that we did individually earlier. We assigned the oxidation numbers. And then finally HCl, it's a covalent compound with chlorine. We said that unless chlorine is the central atom, it's going to be -1, and then hydrogen is +1 in any covalent compound. So +1 and -1 cancel out to give you a sum of 0. So if we look at all the oxidation numbers, phosphorus goes from +5 to +5. Its oxidation number is not changing. Oxygen is -2 on the reactant side. It appears twice, both in POCl3 and water. In the product side, all of the oxygen is also -2. So that's not changing. Chlorine starts at -1 on the reactant side in POCl3. It's also -1 as a product in HCl. So no change there. And then hydrogen appears in a few different places, but it's always +1. +1 in H2O on the reactant side. And in the product side, it appears in both of these acids, and it's also +1. So none of these oxidation numbers are changing, which means that this is not a redox reaction. So whoever said that this looks like an acid-base reaction was actually correct. It's not obvious that that's the case. It doesn't look like the ones that we talked about last time, but this is in fact an acid-base reaction. It's just a different category, slightly different category than what we're used to. But there's no change in oxidation numbers, so it's not a redox reaction. So then part B here, what's the oxidizing agent, is irrelevant in this case because there is no oxidizing agent. It's not a redox reaction. All right, so if you're asked to identify a redox reaction, there has to be oxidation numbers that are changing. All right, the last thing we're going to do is learn how to balance redox reactions. And if you've looked at the review sheet that I made, or the practice test, or I guess practice test isn't available yet, but if you look at the review sheet, you'll see that there are 2 questions on the review that are about balancing redox reactions, and not surprisingly there will be 2 questions on the exam, so you want to learn how to do this because it's 10% of your exam grade. I think balancing redox reactions is a lot of fun. You and I often have different definitions of what it means to have fun, but hopefully some of you will agree with me. And so we're going to learn what's called the oxidation number approach for balancing redox reactions. So in all these cases that you'll see, we'll give you the reactants and products. We're not going to expect you to predict the reactants and products for a redox reaction. We'll give you what they are. You just have to add the coefficients, and then we'll ask you some question about what those coefficients are. Okay, so we just have to learn how to do this, and most of these you're not going to want to try to do by inspection. You know, we learned at the very beginning of Chapter 5 how to balance chemical equations, and we saw that you can take the elements on one side and make sure that they're balanced with the elements on the other side. Most of these redox reactions is very difficult to do that way because not only do the elements have to balance, but the charges have to balance as well. These redox reactions, a lot of times they involve charged species, and if the charges don't balance as well, the reaction won't be balanced correctly. So we have to learn this approach, the oxidation number approach, for doing this. And so the first step in this is to assign the oxidation numbers for each atom. All right, so we have to get good at assigning oxidation numbers because that's an indispensable part of this process. So if we have this reaction here, we have Cl minus plus permanganate going to plus acid H plus going to ClO minus, manganese 3 plus, and water. First thing we have to figure out is what are all the oxidation numbers for every element in this reaction. Cl minus is an ion by itself, so the oxidation number is just the charge, -1. All right, MnO4 minus, we have oxygen is going to be -2 in any compound where it's not bonded to itself or fluorine, as we said. So oxygen is -2, and then if we have 4 -2s from oxygen, that's -8. The overall charge is -1, so that means manganese has to be +7. Alright, so again, quickly doing the algebra to get that. Plus 7, 4 minus 2's, the sum of those would be minus 1, which is the total charge of the permanganate anion. Okay, so whenever you have a charged species, remember the sum of the oxidation numbers equals the charge. H plus, ion by itself, oxidation number is the charge, plus 1. Then we go to the product side. We have ClO minus. If oxygen is bonded to anything besides itself, or fluorine is minus 2. So if oxygen is minus 2, what does chlorine have to be in this compound to balance out the charges and make sure that the sum is equal to plus 1? Okay? So plus 1 minus 2 gives us a sum of minus 1. Mn3 plus, ion by itself, is plus 3. And then our old friend water, plus 1 minus 2. Okay? So that's going to be the first step, figuring out the oxidation numbers for each atom. The more you do this, the more comfortable you'll get with it, and some of them, as I said, are always obvious, like water or ions by themselves. There's no thought involved. Okay, some of these were a little bit tricky, but not too bad. That's the first step. The second step is we have to determine the number of electrons that are gained and lost. For each species. And remember, when we're talking about losing and gaining electrons, we only need to focus on the species that have their oxidation number changing. If the oxidation number is the same on the reactants and product side, that species is not involved in the redox transformation. And so we have to just determine that for the species that changes their oxidation numbers. So what we see is if we look at our oxidation numbers that we assigned up here, Cl minus goes from minus 1 to plus 1. Okay, so that's changing. And the number of electrons that is lost or gained is equal to the difference in the oxidation numbers. Okay, so if we go from minus 1 to plus 1, how many electrons is that? That's a 2 electron change. Plus 1 and minus 1 are 2 apart. There's a difference of 2 between those. So this is 2 electrons. We don't really have to keep track of whether the electrons are lost or gained, but if the oxidation number is increasing or getting more positive, that means we're losing electrons. So this is technically losing 2 electrons, although the number is the important part, that it's 2. And then if we do the other species that's changing, which is going to be manganese, we see that manganese goes from plus 7 to plus 3. So that's going to involve how many electrons? 4. It's a difference of 4. 7 minus 3 is 4. So the change in oxidation number tells you how many electrons are transferred, so that's 4. And because the oxidation number is getting smaller, that means this one is gaining 4 electrons. But again, it's the number that's the important part. Alright, so the second step is to determine how many electrons are lost and gained from each species that changes its oxidation number, and that comes from the difference in the oxidation number between the reactant and the product that has that element in it. Alright, then the next thing to do is we're going to make sure that the number of electrons is balanced. So we add coefficients to just those species to make sure that the number of electrons that are lost are equal to the number of electrons that are gained. I'll write that again because it's kind of squished. Okay, so the number of electrons that one thing is losing has to be equal to the number of electrons that the other reactant is gaining. You can't have electrons created or destroyed. And so if we look at this one again, what we saw was Cl minus to ClO minus. We saw that was a difference of 2 electrons. And then the other one, MnO4 minus to Mn3 plus, was 4 electrons. So we want the number of electrons to be equal. This one is losing 2 electrons, this one's gaining 4. So the way that we do that is we're going to put coefficients of 2 in front of each of these species that are involved to make sure that it's now 4 total electrons. So each chlorine is losing 2 electrons, but now we double that. We put coefficients of 2 in front. So now that there's a total of 4 electrons being lost from Cl minus, and then those same 4 electrons being gained by manganese. So the first coefficients we're going to add are going to be ones that allow us to balance the number of electrons that are lost and gained. And once we do that, we set the coefficients then of all of these species. So we're going to put 1s there to remind ourselves that we're not going to change the coefficients on manganese anymore. Okay? So once you balance the number of electrons, all of those species that are being oxidized and reduced, we don't want to change their coefficients anymore beyond here. And then the last step is to then balance the rest by inspection. So once we've balanced the number of electrons, any other coefficients that get added are just to make sure that the number of atoms are the same on both sides. But we don't change the coefficients that we just added, we just change any other coefficients that might be present. So as we saw, when we balanced this out, we had a 2 there, a 2 there, a 1 there, and a 1 there. Those coefficients we already determined from the number of electrons that are lost and gained. And then we just have to make sure that hydrogen is balanced. And so the way we typically do this is we're going to actually balance oxygen first. So what we have is on the reactant side we have 4 oxygens. On the product side we just have 2 from ClO minus. So we need to have how many waters to make oxygen balanced? 2 of those. So now we have a total of 4 oxygens on both sides. Remember, we don't want to change this coefficient anymore. We've already set it as 2, so we add 2 waters to make sure that we have 4 oxygens on both sides. And then by adding 2 waters, we've added 4 hydrogens to the right side, so we need a 4 H+. So very often the last things you're going to be balancing are H+ and water. You want to add enough water to make sure that the oxygens are balanced on both sides, and then you add enough H+ to make sure that whatever hydrogen you've added from the water is also balanced. Okay, so that's kind of usually the order that things are going to go in. But whatever's left, whatever you haven't already put coefficients in front of, you need to add the appropriate coefficients to make sure that everything is totally balanced at the end. That's just done, what we say, by inspection, the way that we would normally do balancing reactions. Okay, questions on that? All right, let's do a couple more examples because this is good fun and always good to practice. So in this case here we want to balance the following using the oxidation number approach. Okay, so we have dichromate plus iodide plus H plus going to chromium 3 plus I2 plus H2O. Now there's a little bit of a difference here as we'll see, but first let's just assign the oxidation numbers. So oxygen is still -2 when it's bonded to anything but oxygen or fluorine. We have 7 -2s. We have a 2- total charge. So that means the 2 chromiums have to have a total charge of +12 because there's 2 of them, each of them is +6. Okay? So whenever we have 2 identical elements, 2 chromiums, they would have the same oxidation number. So 7 times -2 plus 2 times +6 equals -2, which is the total charge. I- is an ion by itself, so its oxidation number is its charge. Same with H+. Same with chromium 3+. I2 is an element. Remember, any element by itself with no charge has an oxidation number of 0. And then our old friend water +1 -2. Okay, so that's the first step, assign the oxidation numbers. Now, one thing that I like to do is, there's some slightly different ways of doing this, but if we notice here on the reactant side we have Cr2O72-, and each of those chromiums has a +6 oxidation number. And then over here we have Cr3+, which is +3. We have 2 chromiums over here, so we know we're going to have at least a coefficient of 2 there. So whenever especially the species that are changing their oxidation number, chromium we have going from +6 to +3, its oxidation number is decreasing. There's 2 of those over here. There's only 1 on the product side, so I like to put the coefficient in right away. We might have to change that coefficient eventually, but just remind ourselves that there has to be at least twice as many Cr3+ as Cr2O7s because of the differences in the formula. All right, so if we keep that in mind, then for the number of electrons that are involved on the reactant side, we have. We have 2 chromium 6+. Each of those in the dichromate is 6+, going to 2 chromium 3+. So how many electrons is that? It's 3 for each chromium, but then there's 2 of them, so it's a total of 6. Okay, so each chromium is gaining 3 electrons, going from +6 to +3. but because there's 2 of them involved, that's a total of 6 electrons. So when you have situations like this where you have 2 of a specific element that's changing its oxidation number, counting electrons becomes a little bit more tricky, but it's not too bad. And then if we go for I minus, what we see again is the same situation. We have I2 over here, I minus on the reactant side. Move that over a little bit. So we draw a tie line there. Each iodine is going from -1 to 0. So it's 1 electron per iodine, but we need to have at least 2 of them because there's I2. So we can put a coefficient of 2 there, and now this is a 2 electron process. Because it's 2 I minuses going to I2. Each iodine is losing 1 electron, total of 2 electrons for that. And because this is 2 electrons and this is 3, we have to triple all of these coefficients to make them balance. We want the total number of electrons to be the same. So 6 electrons are gained by chromium. We need 6 electrons to be lost by iodine, so that means this coefficient then has to be multiplied by 3. So we're going to have Cr2O72 minus. This coefficient has to get tripled to balance the number of electrons, so we're going to have 6 I minuses. So far we haven't added a coefficient for H+, and then on the product side we have 2 Cr3+. We had to triple the coefficient on I2 to balance the number of electrons, so that's 3I2, and then water. And then as I said, the last thing we'll do is we'll add coefficients to water and to H+ to make sure that oxygen is balanced. So on the reactant side, we have 7 oxygens from Cr2O7, and then so we have to add 7 waters to balance that. And by adding 7 waters, we've introduced 14 hydrogens, and so we get a 14 in front of H+ to balance H+. All right, but again, once we set the coefficients for the species that are being oxidized and reduced, in this case dichromate to chromium 3+, I minus to I2, once we set those coefficients, we don't ever want to change them. But we had to triple the coefficients in front of iodine to make sure that the number of electrons lost and gained was identical. All right, questions on that one? All right, let's just keep doing it. We have balancing this one and determining the sum of the coefficients, so a little bit different question in this case. So we have KiO4 plus ammonia going to Ki, N2, and water. So we're going to assign oxidation numbers. KiO4 is an ionic compound, potassium periodate. So the potassium is going to have the same charge that it always has in ionic compounds, which is +1. Oxygen in any polyatomic is going to be -2. And so if we have a +1 and 4 -2s, iodine has to be +7 to balance those out to be 0. Iodine is in group 7, so it cannot have an oxidation number greater than +7. That's its maximum oxidation number. NH3, we have hydrogen in a covalent compound, so it's going to be +1. If we have 3 +1s from hydrogen, this has to be -3 to balance that and add up to 0. On the product side, we have Ki. This is just a simple ionic compound, so it's going to be the charges, which are +1 and -1 for potassium and iodine. Potassium is group 1, iodine is group 7, so +1 and -1. N2 is an element, so we can quickly identify it as 0. And then water +1 and -2. We've seen that in all these examples. All right, so this is another case where we have, again, if we look at the changing oxidation numbers, iodine goes from +7 to -1, and then nitrogen goes from -3 to 0. However, we notice that on the product side we have 2 nitrogens that have the 0 oxidation, say N2, so we can slip a coefficient of 2 in front of there to recognize that there has to be 2 nitrogens changing their oxidation states from -3 to 0. So if that's the case, we have 2 nitrogens each changing by 3 electrons, going from -3 to 0, difference of 3, which means this is a 6 electron process in total, and we have 2 NH3s going to N2. And then for iodine, we don't have to add any coefficients, but we see that the oxidation number changes from +7 to -1. That's a difference of 8, so there's going to be 8 electrons there. So we have 8 electrons in one part of our redox reaction. We have 6 electrons involved in the other. So how do we get these to balance? We need to find the least common multiple of 6 and 8. which would be, what's 24, yeah. No, I knew that, I'm just making sure you guys do. So we have 6 and 8 is, so if we multiply 8 by 3, we get 24. If we multiply 6 by 4, we get 24. If you multiply the two together, 48, that would work, but then you wouldn't get the smallest whole number coefficients. You have to reduce them after that. So this, if we triple this, that gives us 24 electrons. And if we quadruple that, that gives us 24 electrons. So we're going to add coefficients of 3 in front of KiO4 and Ki. And then the coefficient in front of nitrogen we have to quadruple because we need to make that a total of 24 electrons. So that too has to get quadrupled to an 8, and this then becomes a 4. All right, so again, we need to make sure that the number of nitrogen is still balanced. That's why this is an 8 and this is a 4. So we get 3 KiO4 plus 8 NH3 goes to 3 Ki plus 4 N2, and then the last thing that we have to do is just add water. And so figuring out how many waters we need, on the reactant side we have 12 oxygens, 3 KiO4s is a total of 12 oxygens. So that gives us 12 waters, and then we can verify that hydrogen's balanced as well. We have 24 over here, 8 times 3 is 24 over there. So we just have to add a coefficient of 12. And then the sum of the coefficients would be 3 plus 8, which is 11, plus 4 is 14, plus 4 is 18, plus 12 is 30. All right, so the sum of the coefficients, which is what we asked for here, would be 30. So you can see that a lot of times redox reactions we have pretty big coefficients. It would be pretty difficult to do this just by inspection, and so using the oxidation number approach will ensure that we get this right every time. All right, we're going to do one last one here, just to wrap this up, where the only difference here is there's one little thing we have to add, as we'll see, to balance this one. We're going to follow the same approach, but there's just one extra little thing that we'll sometimes see that comes into play here. So we're going to balance the following and determine the coefficient for HNO3. So we need oxidation numbers to start with. Zinc is an element by itself, so it's 0. We have nitric acid, covalent compound, so hydrogen will be +1, oxygen -2. That leaves a +5 for nitrogen. So 3 minus 2 is from oxygen, 1 plus 1 from hydrogen is -5. +5 balances that out. Zinc nitrate is an ionic compound, so the charge on zinc is going to be +2. There are 2 NO3 minus anions, so the charge on the metal is +2. So in any ionic compound, the oxidation number for the metal is the charge. Then we have NO3 minus. We can treat that as a unit. So for NO3 minus, we have 3 oxygens that are still -2, and then nitrogen would still remain as +5. Now a shortcut to think about this is we see here we have nitric acid HNO3. We're losing a proton to make NO3 minus anion. If you just lose or gain protons, you don't change the oxidation number. And oxidation numbers refer to losing and gaining electrons. So we can quickly determine that if nitrogen starts as +5 and oxygen starts as -2 in nitric acid, it would be the same in nitrate. We could also do that the long way and recognize that NO3 minus is the anion. And if this is -2, this has to be +5. So there's a couple ways of getting that one, but we get +5 and -2 still for those ones. We have NO here, binary compound, oxygen -2. Nitrogen would have to be +2 to balance that. And then for water, we have still +1 and -2. Okay, so those are the oxidation numbers. Now there's a couple of, and then we want to look at the ones that change. We identify those. We have zinc. Let me erase that, it's just in the way now. Zinc goes from 0 to +2, so that's a 2 electron change. And we also see that we have a nitrogen here that's +5 and a nitrogen that's +2. So that's 3 electrons. +5 to +2 is a difference of 3. However, we also notice something else here, which is that some of our nitrogen is starting at +5 and is remaining at +5 on the product side. So for HNO3, some of this is serving as the oxidizing agent. It's getting reduced to NO, changing its oxidation number from +5 to +2. But some of the nitric acid is just supplying NO3 minus counterions to this product here, and the oxidation number is not changing. So whenever we have a situation like this where we have an element where some of it is changing its oxidation number, some of it is not, we notice that some of the nitrogen in this reaction does not change its oxidation number. And so whenever that's the case, the way that I like to do this is we're going to divide this HNO3 up into two portions. One of the portions we're going to balance using the oxidation number approach and the number of electrons that are lost or gained from it. The other portion we're going to balance at the end by inspection once we've balanced all the electrons. So we're going to rewrite this out as zinc. I should give myself room to write coefficients because I will need those eventually. We're going to write out HNO3 twice, and we'll see why we do that here in a second. We have a product that's zinc nitrate, NO, and water. And so again, zinc goes from 0 to +2, which is a 2 electron. And then nitrogen, this one goes from +5 to +2, which is 3 electrons. And so when we want to balance out the number of electrons, we have to add coefficients. So we're going to triple that because we need to balance the number of electrons to make it 6. We double that to also make it 6 electrons. So this zinc and the zinc nitrate get a coefficient of 3, and then this nitric acid gets a coefficient of 2, and NO gets a coefficient of 2. All right, and then our last step is going to be to balance the rest of this by adding coefficients to nitric acid and water. And so what we notice here is that on the product side we have 3 zinc nitrates. So we have a total of 3 times 2, which is 6 NO3 minuses. So we need to add 6 more nitric acids to supply those NO3 minuses. So these 2 HNO3s are being reduced to NO. These 6 are just losing their proton and becoming NO3 minus. So we balance them separately because only the things that don't change your oxidation number are we going to balance at the end by inspection. And now we have to check on the number of water molecules that are involved. So these 6 nitric acids aren't losing any oxygen, but these ones we're going from NO3 to NO, so we're losing 2 oxygens each. So we're losing 4 oxygens from this, and those go then to make water. So we put a 4 there. And so finally, when we simplify this, we get 3 zincs. We can recombine the HNO3s now at the end. 2 plus 6 is 8. And then we have a 3 in front of zinc nitrate. A 2 in front of NO, and then 4 waters. And so the coefficient in front of nitric acid, which is what we were asked about, is an 8 in this case. So it's possible you can figure out how to do this without dividing it up like I did, but I like to do it that way because once I set the coefficient on the species that's getting oxidized or reduced, I never want to change it again. And so I balance this one separately at the end to make sure that I never have to change that coefficient and screw myself up. So you could have possibly done this by inspection with just, without dividing up the HNO3s into 2 piles, but I like to do it this way, and hopefully that makes a little bit of sense. Okay, so any questions on balancing redox reactions? All right, the last thing we're going to do in Chapter 6, which we'll start today and finish next time, is solution stoichiometry. And the way your book does it is they introduce this topic pretty much in every section for each type of reaction, but really it's the same concept every time. So we already know how to do stoichiometry very well from Chapter 5, and the key concept from this is that moles are the quantity that we need. Okay? So whenever we're doing stoichiometry, our first goal is always to convert into moles. So moles are the key quantity of whatever reaction or product we're interested in. And then once we have moles of one species, we can use molar ratios to convert moles of one thing into moles of another. So that is still true for any of these types of problems that we label as solution stoichiometry. The difference here is that we're going to very often use a different relationship that involves moles. So in Chapter 5, we learned 2 relationships for moles. One of them was molar mass, which allows you to convert grams into moles or vice versa. And then we also learned Avogadro's number, which allows you to convert number of atoms or molecules into moles or in the other direction as well. The difference is when we're doing reactions in solutions, very often we're going to use molarity as a conversion factor that involves moles. So as an example, if we want to know how many moles of sodium chloride are in 236 milliliters of a 0.524 molar solution, we can use this molarity, 0.524 molar, as a conversion factor to determine the number of moles. Because we recognize the definition of molarity that we learned earlier on in this chapter is that it's moles per liter. So this solution would have 0.524 moles of sodium chloride per 1 liter of solution. That's the definition of molarity. So this is another conversion factor then that involves moles that we can add to our toolbox when we're doing stoichiometry. A shortcut that I often like to take, because in many cases solution volumes are reported in milliliters and not in liters, is that this is equivalent to moles per 1,000 milliliters. Okay, 1 liter is equivalent to 1,000 milliliters. So very often you'll see that I'll rewrite molarity in this fashion, because in most problems the volumes of solution that we're using are on the order of milliliters and not liters. Liters is kind of a comically large amount of solution to use in a laboratory setting, so usually, as you'll see in Chem Lab, you'll do things on the scale of milliliters, not liters. So in this example here then, if we want to find the moles of sodium chloride in this solution, we start with a given volume of 236 milliliters of that solution, and then we just multiply it by the molarity, which is moles per liter, so 0.524 moles of NaCl per 1,000 milliliters. So milliliters cancel out, and that gives us a molar amount of 0.124. Okay? So this is really the only thing that we're going to introduce as a new concept when we're doing solution stoichiometry problems, is that when we're finding the moles of a reactant or a product, in many cases we're going to use molarity as a conversion factor that allows us to go between volumes of solution and moles. Other than that, everything is pretty much identical. So then that allows us to expand the flowchart that we had. So we did this flowchart sometime during chapter 5 to explain stoichiometry. So what we saw in chapter 5 is that we're usually starting with a mass amount of one reactant, and if we have the mass, we can convert into moles using the molar mass. And then we can also do the same thing for the products. And so once we have the moles of one reactant, we convert between those using the reaction coefficients. Which are those coefficients out front of each species in the chemical reaction. And then if we want to find the mass of the second species B, whether it's another reactant or a product, we use its molar mass to convert between mass and moles. So that's what we learned in chapter 5. The other thing we learned in chapter 5 was using Avogadro's number. So if we want to know the number of entities of A, where entities would be either the atoms or the molecules of A that we have, we can convert between those using Avogadro's number. And same thing for B. If we want to determine the number of entities of B, where that would be the number of atoms or molecules, depending on whatever the fundamental particle is that makes it up, we can use Avogadro's number to do that as well. So that's all chapter 5. That should be a review now. And the only difference now is that in most cases when we're doing solution reactions to aqueous solution, we're going to have a volume of an aqueous solution of that reactant or product. And we're going to use the molarity to convert between moles and volume. And the same thing for whatever other species we want to convert between. We're going to have a volume of that aqueous solution, and we're going to use molarity to convert between volume and moles. Okay? So the key linchpin is still the same. We have to get to moles of reactants or products to be able to convert between them using the coefficients, but now we have another way of doing that. Okay, so people get, it's not really that big of a leap of faith now. We're using things that we kind of already know, and we're just adding them back in to do stoichiometry problems. So let's see how this works. Let's do at least one example before we close up, and we might get to both of these. So we want to know what is the identity and mass of the precipitate that is formed when excess calcium chloride reacts with 250 milliliters of 0.555 molar silver nitrate. All right, so our first step is going to be to write the reaction or the equation. So we're taking calcium chloride and silver nitrate. Both of these are aqueous solutions. Anytime you see the descriptor molarity, you would assume that's an aqueous solution, because that's the only time we use that. And then the products, again, this is an ion exchange or a precipitation reaction. So the cation from one pairs with the anion from the other, so it's going to be calcium nitrate. All nitrate salts are soluble, and then the other product, we're going to take silver, Ag+, and pair it with Cl- to make silver chloride. And that we should recognize is a precipitate. It's insoluble, so it forms a solid. So that's the identity of our precipitate. We have to add a couple of things to balance this. So because we have 2 chlorines here, we need a 2 in front of silver and a 2 in front of silver nitrate. So small coefficients to balance this. But we get a 1 and 2 and a 1 and 2. So that's the balanced chemical equation. We could also write a net ionic if we wanted to. Which is just the 2 ions that combine to make the precipitate. So when you're doing solution stoichiometry problems, typically you could use either the full equation or the net ionic equation, but the full chemical equation is often more convenient. So we could use either of these, but usually the formula, or what we call the molecular equation, the full equation that has all of the species written in full. So if we're doing a stoichiometry problem, usually we'll just use that first form of the equation. We don't have to necessarily write out the net ionic, although we could use it if we wanted to. Okay, but this is our balanced chemical equation. We've identified the precipitate, which is AgCl. And so then the next step to solve this problem, which is the last thing we'll end with today, is just determine the mass of AgCl that forms. Alright, so our balanced chemical equation is, again, this here. Alright, so that's just rewriting what we did in the last one. And what we're looking for is the mass of AgCl that forms as a precipitate. And so what we're starting with is 250 milliliters of silver nitrate solution. So we're starting with 250 milliliters of solution. The first step in any stoichiometry problem is to convert into moles. And for solutions where we have the volume and the molarity, we're going to use that molarity to get moles. So we have 0.0555 moles of silver nitrate per 1,000 milliliters. That's the shortcut that I use for molarity when we're given milliliters. Alright, now that we have moles of one species, we can figure out the moles of the other species, AgCl, that forms. And so if you look at the balanced chemical equation, 2 moles of AgCl form for every 1 mole, or sorry, 2 moles of AgNO3. We're doing AgNO3 in this case. So it's a 2 to 1 mole ratio, or sorry, 2 to 2, I keep saying 2 to 1, sorry. 2 to 2 mole ratio, 2 moles of AgCl for every 2 moles of AgNO3. That comes from, again, these coefficients here, 2 and 2. And then finally we have moles of AgCl, but we're looking for the mass in grams. And so the last thing to do is use the molar mass, which is, I won't calculate it for you here because we're running out of time. The molar mass of AgCl is 143.4 grams per mole. And so we multiply that to go from moles back into grams. So moles of AgCl cancel. And then what we calculate is that we should get 1.99 grams of silver chloride. All right, so it's very similar to any other stoichiometry problem. This key step here of using mole ratios is the same, but very often for solutions we'll start with molarities and volumes and use that. All right, next time we'll finish up some things with solution stoichiometry and what are called titrations, and then we'll move into chapter 7 in the beginning of that.